Yes, I understand that from your side, maybe you can't see the mouse pointer. In fact, you actually can see no problem with the mouse pointer, but the problem comes when I don't use the mouse, which most of the time I do in the presentation mode. I switch to my electronic writing pad, okay, connected to an USB, and you know it. So I use a pen and kind of like what do you call it, digital pen, a digital pad. So that helps me to write on the screen. For that one, I'm sure exactly whether I can do it or not. But if you too have that problem, just bear with it. I will try to fix it because it's a random thing I bought online from Shopee, from Tiki, and let me see if I can do it or not. All right. So we were writing here. But now the first thing, as usual, I'd like to know where we were exactly, in which part. Let me scroll down as best as I can remember. We finished LFS, JFS, and BFS. Is it true? I think we came up to that point, but still I need a reconfirmation from your side. We talked about these things as best as I can remember. Log structured file system, then the journaling file system, which is equally important. There's a whole bunch of the slides. I didn't show you the slides. JFS, and finally PFS, a virtual file system. So are we supposed to get started from here? Can anyone confirm? Are we supposed to get started from here? Anyone? Oh, someone sent me a message. What is file system performance? Okay, there we are. Where was, oh really? We did move in. All right, that's good. Most of the others, I remember we were just getting started from this point. It's good. So we are a little ahead of others. So file system performance. Performance depends on a couple of things, as we understand. First of all, the faster access. And well, in fact, it all comes down to that, the faster access. But for faster access, we have, we already talked about a technique that we often use to make things work much faster. And that is usually the cache. Okay. So most of the time we talk about the cache. Having a cache will always enhance the performance. So that's the first thing that we talk about. Along with cache, so we move through all these things. I will go there. There we are. So the first thing that you're going to learn is how can we manage the cache and what do we do inside our cache to make both random access and sequential access faster. Of course, cache is there to make things faster, right? But still, there is a trick that we can play depending on whether a file is being read sequentially or randomly. If we can figure it out, then we can most likely put it in the right way. I mean, we can try to manage it, as we call it. Okay. That is what we're going to study. And later, moving on, I will just show you the slides that you can see that moving on will essentially end up right here. And this is where we will have to move to the next part, which is, again, very interesting to understand this little part, because this little part will be directly associated with the hardware. So you need to understand the hardware structure and how the controller controls the hardware. Okay. And as I said repeatedly before, that file system maps the file on the hard disk, but it's the controller that logically interprets each part of this hardware in its own way, because the controller is coming from someone somewhere else, and your OS is coming from somewhere else. So there needs to be an understanding between them to make things happen. Well, we'll see it in a moment when we go there. So let's talk about cache. Block cache and buffer cache. Many file systems have been designed with various optimizations to improve the performance. There are two different kinds of caches, the block cache or buffer cache. Is a collection of blocks that logically belong on the disk but are being kept in the memory. These are blocks, okay, but they're kept in the memory. Now, as for example, that when we were talking about the directory search, we mentioned that caching and hashing, these were the two techniques that we could use to speed up the search of a directory. And to do that, we basically created another directory, a kind of cache directory, and we started storing it. And always, wherever we find this cache concept, like even when we talked about TLB, okay, you remember translation look aside buffer was a kind of hardware cache. In memory management, MMU, inside of it, we always try to put it, okay, small, keep it small. We keep it small because programmatically, anywhere, even your software cache, your browser cache, for example, wherever you see cache, you must remember that it logically belong to the disk. But physically, when your computer is running or when that app is running, that particular thing must stay loaded on RAM. Because the whole concept comes down to the same thing. Anything that you access from RAM, it is 50 times faster than anything that you try to access from the hard disk. That is the underlying concept. Check all read requests to see if the needed block is in the cache, if it is accessing without disk access. Otherwise, reading into the cache, then copying whenever it is needed. Okay. Read requests to see if the needed block is in the cache. If it is accessing, now at this point, you have to understand the read requests are coming block by block. So you can check all the read requests and put them in the cache straight away, right from the beginning, if it is accessing without disk access. What I mean, specify that they're doing it in a sequential way. Otherwise, reading into cache, then copying to whatever it is needed. So basically, either you do it serially, sequentially, or you do it in a random way. To access quickly, the hash table and the linked list is used. All right. When a block has to be loaded into a full cache, the usual page replacement algorithm is applied. That's the LRU, least recently used, is applied. Even right here, because you're going to put that block into the memory. All right. So that's why we go back to memory management a little bit. Block read ahead. So please remember, as we mentioned before, that there can be two different patterns of access, right? The first one is sequential. The next one, the second one, is what we call random. So block read ahead is a sequential approach. The point is the file system can keep track, as you see at the bottom first. The file system actually can keep track of the access pattern to each open file. Initially, the file is given the sequential access mode. Whenever a seek is done, the bit is cleared. Sequential reads start happening again, the bit is set once again. So basically, both of them work together, and the file system on a single file, okay, can switch from sequential mode to seek mode, to read mode to seek mode. Like here, as they say that we start with a block read ahead. So try to get blocks into the cache before they're needed to increase the hit rate. That is the whole concept. Many files are read sequentially where the file system decides to produce block K in the file. It does that, but when it's finished, it makes a sneaky check in the cache to see if block K plus 1 is already there. Because as we understand right at the bottom, you can see, bottom of the screen, I said the file system can keep track of when a file is being accessed in a sequential manner and whenever there's a random pattern of access. And again, it switches back to a sequential pattern of access, and the bit will be changed. Yeah. So that is exactly how it keeps track of these different modes of access into the cache before they're needed to increase the hit rate. Many files read sequential. So the concept is when a K block number K is required, it is loaded, but the file system will do a sneaky check to see if K plus 1 is already there, because at this very moment, this file is being accessed sequentially. So naturally, if currently they need to read block K, the very next thing they will be looking for is K plus 1, block K plus 1. It's quite obvious, right? If it is a random access, as I mentioned, that there are two ways to go for that. If it is seek operation, that means the file is being accessed randomly, right? Then we have to apply certain algorithms. The things will be a little bit more complicated, not like sequential. What we do is basically to reduce the disk arm movement. The disk arm movement, and that is what we try to reduce. And we will have a whole bunch of algorithms in the next part where you will see that what we can do to reduce this. Well, this is the one that it was talking about. Now, how to So we can basically try our best to reduce the disk arm motion. To understand this part, the moment I will just highlight a few words, but we need to move back to understand the disk structure and what is what. I mean, for example, they have mentioned the word cylinder. Of course, we may have heard about cylinder before, but I mentioned it. But what it is. Okay. So we need to understand the hardware structure, the underlying hardware structure a little bit before we can dive in. What happened? I think it's my pen. Google Chrome is not responding. Goodness me. Wait a minute. Early in the morning. Let me see what happens. So, at least for quick reference, you remember the block read ahead is a technique that of cache management that is used to improve the performance of the file system, okay, for sequential pattern of file access, when the file access pattern is sequential. But when the file access pattern is random, then of course we use a different technique. And the technique that we use is all about disk arm movement to reduce the disk arm movement. That means how far it could go to get displaced. We will see it in a minute, and probably with another bunch of slides. Okay. Can you give me the presentation? Okay, at last. So that is what we're talking about. At first, blocks that are likely to be accessed in sequence close to each other. That is a logical solution of this one. Okay. And as to say, preferably in the same cylinder. But blocks that are likely to be accessed in sequence close to each other, preferably in the same cylinder. That is where you have to wait a little bit until we go to the next part and we understand what a cylinder is and how these can be accessed. And in fact, we will end up in that chapter with some wonderful algorithms, a handful of lovely algorithms and very important algorithms. Those are the algorithms that will be used for cache management and for performance improvement. Basically, that is exactly what we're talking about, to reduce the disk arm motion. Okay, so essentially how it works, I can give you just a lead here, although we will see it. In fact, if you have access to YouTube, you can go there and you can see how hard disk works. So hard disk, a kind of stack of disks that you have. Okay. And these are what we call platters. Then there's a spindle, that is a spindle that revolves. Okay, that's an axis that keeps rotating at a high speed. And that high speed is what we call, what is measured as RPM, by RPM, that rotation per minute. And there we have an arms assembler. It has several read and write magnetic heads. And these read and write heads are the ones that do the job of writing. So as you can imagine, let's show it right here, you can imagine as these platters, this stack of disks, keep moving at a very high speed. These read and write blocks, they keep just zooming in and dump some data blocks, dump some data in a block, and then move back. Then go there and move back, go there and move back, go there and move back. It's more like, if you think of this one as read and write head, is just moving in right here to write something, then move back again, then go there. And remember, it is just moving this way and that way, this way and that way. It's not changing its position because it doesn't have to. All it has to do is to sequence its move in such a way that that part of the disk, because the disks are moving. So disks are moving means that the different parts of the disks are actually passing through the head, passing under the head. So when it is there, and that read and write head will just zoom in and dump the data and move back. So it's a wonderful technique. I think you can take a look at the video, or if you can't see it, just go to YouTube and search for it, how hard disks work. Okay, you have to crack it open and look into it, the hardware. Because that concept will help you to understand the structure, the following things that we are going to talk about. In group of consecutive blocks, and so basically put the inodes in the middle of the disk rather than at the start, thus reducing the average length of the inodes, the first block. So the proposal that they have given is this. If you put them all on that side, then it will take a longer time to cover. Again, this is, say, for example, this is your read and write head. So you see, read and write head will have to wait for a long time. So basically, if you put your inodes like this on one single cylinder, but if you put them on multiple cylinders, into cylinder groups actually, and each with its own inodes, and then the actual displacement of the arm, this is the arm, okay. Displacement of the arm has been reduced. Compare this displacement of the arm and this displacement of the arm. All right, so that is one of the things that we do, but it is purely from the hardware perspective. So in general, you should remember that there are two approaches. One is sequential, one is random. In the case of random, we have to reduce these arm movement. Reduce disk arm movement to improve performance. In the case of sequential, block read ahead. Okay, so that is what we do. Now there's something that you can see, cylinder. This is something that you need to understand, that I think I mentioned before, but I'll mention it once more. You can't see the cylinders like that. when you open your hard disk, you crack open your hard disk, take a look inside of the hard disk, the hardware, you will see a stack of CDs, basically platters, disks. And you will also see the spindle. You will also see the arms assembler and the read and write heads. Probably you understand that each disk is associated with a top surface and a bottom surface. So there will be basically two read and write head per disk in the platter, in the stack of platters, the stack of disks. Okay, so these are the pure hardware that you'll be seeing. But why is cylinder? And we are referring to it as cylinder. Now, cylinder is a logical grouping. Remember, there are words like cylinder, sector, track. So my question is, if you look at the actual hardware, will you see cylinders? Will you be able to see cylinders now? Will you be able to see the sectors now? Will you be able to see the tracks now? So this is purely a logical interpretation of the physical space once more, but this time this is done by a controller, the disk controller. So everything, remember, and who is communicating with the controller? It's the file system that needs to communicate, because without going to the controller, you can't reach the actual hard disk. This is an I/O device, so we need an I/O controller, a disk controller. Now, when FS wants to communicate something with the controller, so FS needs to be aware, a file system needs to be aware of the cylinders, sectors, and tracks, the way it has been arranged. Okay, so whether it should be stored right there in multiple cylinder groups or in one cylinder group. So these are some of the key parameters, you see, that will make the difference. That will definitely make the difference when it comes to when it comes to its application. Okay, so that is what we are looking at. The next thing about the system performance is defragmenting a disk. Now, how do we defragment the disk? So that is what we're going to study. Defragmenting disks, as I was talking about, was something that was very common. And in fact, yes.
No.
So the point that we were talking about, like defragmenting deep. In defragmenting disks, in our times, it used to happen a lot. So, in the defragmenting disks, one of the key things that we have to remember is that we can't do compact. Remember, compaction is the most common word that we're using when we are talking about defragmentation, or rather compressing these fragmentations in memory management. That was okay because we could easily change the relative position. Of course, it was expensive, as we say, so it's too much of extra work for CPU. But still, we could actually do that because all CPU had to do is to recalculate the base values of all the processes currently on RAM. And they will just try to compress and merge all these. First of all, they will have to push all these fragments together, push it uh, into the outskirts, and then combine them together, merge them together to make a larger whole. That was compaction. But here you can't apply that because everything has been written. Once written, it's written. Of course, I mean, it does take a lot of time. It's an I/O after all. So if you want to defragment it in that way, compaction won't work. Well, the only way compaction may work is just right from the beginning, asking people not to write, not to overwrite, not to edit, not to save, not to delete. The kind of things that we did, kind of restrictions that we imposed on disks. I mean CDs. That's why we used to call them compact disks. But that's not possible. Now at times, defragmentation was always a problem, and for disks, we used to go for formatting. Now, formatting literally means maybe some of you have done formatting. I'm not sure. And you see, when you go for formatting, that means basically you choose a drive that you want to format. Well, don't do it because it will delete everything. It has to delete everything. Because you right click there, and the first thing you said is click on format, and there are a couple of messages. The first message that you get says, are you sure you want to format? Because all your files will be deleted. Okay? You agree or not? If you agree, if you say yes, that's okay, all right, go ahead. The next thing that they will ask you is which file system, if your computer is your OS supports multiple file systems, which file system you want to use to format it. So what exactly formatting is? Formatting is literally remapping because that part of the drive got too cluttered, okay, too messy, and it's all holes here and there. To understand it, use a simple analogy. Just you want to set up a classroom or something, you get in there and you open the door and you see all the tables and chairs and benches and everything. They are kind of like heaped on each other, piled on each other in a random way. So you have no sense of space. Of course, you can see pockets of space here and there, but those spaces can't be utilized because everything is a big mess inside the room. So what will you do? The very first thing that you do is to ask someone to help you to pull all the benches out, all these clutter out of the room. I want to see the empty space. And once you have the empty space, now slowly you can reorganize right from the beginning every little item that you want to put in that room. Okay, so basically that is formatting, because you can't do any mapping unless you clean up the entire space. You have no perception of what is free space and how much of free space you have, or how much of space is being used currently, is being occupied. So that's why defragmentation is one of the key things. Disks become badly fragmented with files and holes all over the place, giving poor performance when new file is created. Moving files around make them contiguous, and to put all the free space in one or more large contiguous region of the disk. Well, that's what we can think of. Now we will be talking about a couple of different kinds of systems, file systems, and which over the time became popular. For example, the one that you're looking at, example, the file system, Cd-Rom file system, which they call CD-R. And in fact, this is the one I was talking about. Like we call it CD because right from the beginning, we put some restrictions on how to use it, and thereby we hope to achieve non-fragmentation. I shouldn't say defragmentation because literally you can't apply fragmentation, or you can't force CD to get fragmented. Okay, that is what we had. The CD-ROM, it could be CD-ROM R, CDR, that means again writable. Well, even in the case where there were a couple of variants there in the market, most of the CDs were just one-time write, but there were some CDs that were rewritable. But rewritable CDs doesn't mean that you can open one of the saved files in the CD and overwrite it. Well, that means make it fatter. Well, you can add more files to the CD. That's what we call rewritable, okay, CDs. And we are quite familiar with that. And we had it's followed the ISO 9960. Okay. That was an international standard in 1998. Joliet extension, that was an extension made by Microsoft. So sometimes in the exam, we do ask about Joliet extensions, a very basic thing. Is invented by Microsoft, were designed to allow Windows file systems to be copied to CD-ROM and then restored in precisely the same way that Rockridge was designed for Unix. As I say, as you move in, you will see that much of what Microsoft introduced, well, kind of like they did their own share of re-engineering or reworking on some of the basic technologies that were introduced earlier by Unix, chiefly by Unix. Okay. The Joliet extension fills the long file names, Unicode character set, directory nesting deeper than 8 levels, and directory names with extensions. In fact, we can read the CD-ROMs, and basically, until recently, now of course, everything you download from their server straight away because internet is so popular and so readily available. Okay. But in our times, when you want to get an OS, it must come operating system. It must come in a CD. Okay. We were always asking for the CD. And the CDs, everything, the software, operating systems, we were given a CD or a bunch of CDs. So that is where they had to re-engineer that system so that they could easily copy those things into their OS basically into their CDs. That's what they did with a Joliet extension. MS-DOS, they used to use FAT. Okay, as you can see right here at the bottom. FAT in memory. First, an open system call to specify a path that is looked up component to component until the final directory is located and read into the memory. Fixed size 32-bit directory entry. File names 8+3 stores the file size as 32-bit number, can be large as 2 GB and keeps track of the blocks via a FAT in main memory. Could be FAT16, could be FAT32. In earlier versions, we had FAT16 and then we had FAT62. Unix V7 file system is another important one, and that one, basically, this is the one that introduced, so Unix was the first one to introduce this wonderful concept of inodes. That much later, around 2000, Microsoft adopted that technique and in their own new file system that is called NTFS, New Technology File System, just essentially modeled after Unix V7. Right. Form of a tree starting at the root directory with adding to links, coming at directed, a cyclic graph. File names are up to 14 characters and can contain any ASCII characters except null. Entry contains one entry for each file in that directory, including file name, and the number of inodes will take 2 bytes. Each entry is extremely simple because it uses the inode that can contain some attributes. So basically, the structure was a little bit different. As I said, the concept was introduced. As you can see, it looks very similar to, absolutely similar, basically. Okay. Nothing different. This is the same thing, this is like the same picture that you're looking at that we saw earlier with Microsoft NTFS. So these are some of the key things that we studied right here. We talked about directories, file system implementation, file system management optimization issues, a few issues, and example of a few file systems. So once we get to that point, then we will move on, because they are kind of related to each other. We will rather talk about disk at this stage. Although disk basically belongs to I/O, but there is no harm talking about disks at this stage. I think this is better. Wait a minute. Okay, Tuesday, this I/O, it basically belongs to the I/O part, but there's no harm in it. I/O will be the next chapter. So if you study it here, it's even better, because this will give you the idea of what we meant by reducing disk arm movement in an algorithmic way when the seek operation happens, and thereby basically improving the performance, the file system performance. Okay, so to understand it, before we go, we started, I would like to show you a picture. Well, this was in 1956, the IBM RMac, as you can see, a stack of disks. 80,000 times more data on the 8 GB 1-inch drive is right hand than on the 24-inch RMac. That was right. So see what difference, how the things are changing. The relative size is going down, and where was this one, and where is this one? It's right hand. Anyway, this is the picture that we will have to remember. That's the one that we were talking about. So what we see right here is that we have a spindle. Now, when you crack your hard disk open, this is what you're going to see. And you can see that we also have the concept of cylinder. Now, this concept of cylinder, as I said, it's a logical concept. As such, when you break it open and you look into your hardware, the actual hardware, you can never see the cylinder. Okay, you can never see the sector. You can never see the track. These are logical interpretations done by your controller, the disk controller. Okay, so we have the ARM assembler, and for each platter, they call it the platter, in the stack of disks, we have the upper layer and the northern layer. So basically, two of them. Okay, they were trying to locate each other. They were trying to read and write simultaneously. And these heads, these read and write heads, move independently. So the question that we raised, that how can we reduce the disk arm movement? So basically these arm movements, we can do it by logically putting these cylinders closer to each other. That's what we say. I might say, so wait a minute, how can you do that? Well, we can probably do it. If we can keep track of those blocks, and we can do it because the cylinder, the concept of cylinder itself, is a logical concept. So it doesn't matter if 5 is next to 50. Try to understand. This is a logical thing. So 5 is next to 50. It's two cylinders. That means two parts is a mapping, right? So there are two parts next to each other, two blocks next to each other. You refer to one block as 5, the other block as 50. So that's what we mean, that we put them conceptually closer to each other. Okay. And the most interesting thing is when it comes to reading or writing, you can see the way the file system will communicate to the controller is to cylinder number, surface number, sector number, of course, transfer size, and memory address. Memory address means where it should be read from. I mean, the RAM address, where the data pages are, or where exactly these data pages, these data blocks should go. That's the memory address. Okay. Transfer size, how much of data you want to transfer, either from disk to RAM or RAM to disk. Cylinder number, surface number, sector number. Cylinder number, surface number, sector number, but the cylinder number and sector number and also track number, these are logical things. Okay, so these are the two core concepts that you need to understand and need to remember to get into this part. Of course, to start with, we will talk about RAID levels. Okay, how these RAID levels work. But before we come to the RAID level, I think it would be more relevant if we can jump in a little bit, skip and go straight to, you see, this is all related to I/O, but no worries, because I/O will not interfere in this part. We'll talk about disk arm scheduling algorithm, because this is the most interesting part, and you understand that in the previous slide when we were in this part and we were talking about disk, right? Reducing disk arm motion. If you want to reduce disk arm motion, then obviously the way to go for it is to change or choose the best of these disk arm scheduling algorithms, because the scheduling algorithm is that will help you in trying to resolve that issue of time. We want a faster access of all these random blocks, cylinder blocks. So how can we do it? So we'll rather go there and see it for the first seed first, and then we'll come back and talk about something else. So this is all about disk. Okay. Then we'll talk about RAID. There are three things in this part. One is that one is RAID, and also a few other things that we do on disk. So this part is all for disk. Since the disk, disk logically belongs to I/O, but it is logically belongs to I/O, but it always is a part. It's a part of